In Chapter 10, we're looking at linear regression. We want to find out if a relationship exists between two quantitative variables. And most of the work that we'll do on our calculator because it would be very tedious to do by hand. The first thing we need to establish is visually if there appears to be a linear type of relationship amongst the variables. To do that, we're going to prepare a scatter plot on our calculator. We'll put our x values in one list and our y values in another list. This is paired data, so you want to keep in mind that the pairs need to stay together. So, you can rearrange the pairs, but 139 needs to be the length that goes with the weight of 110 and so forth. By the way, these represent the lengths and weights of, I believe it's 12 black bears. So what we're going to do is go ahead and put that data in our calculator in the list. So I'll go to Stat, Edit. Okay, and I'm going to put the data in the list. So I've got 138, 139, and in the second list, I'll put in the other variable. All right, so I've got my variables in my list. The next thing I'm going to do is set up my stat plot. So I'm going to get out of here by doing second and quit. And I'm going to go to stat plot. So I'm going to hit second and the y equals key. All right, and right now you see all of these different plots that we could set up. Right now, all of mine are off. I only need one of them to be on, and it really doesn't matter which one. So I'll just choose number one. If you already have one that's on, then you can go on and use that one. Or if you have more than one that's on, then I'll show you how to turn it off. But I'll select number one. And then the first line is where we can choose to turn it on or turn it off. Right now, off is highlighted. So I'm going to hit enter while my cursor is blinking on, and that turns on this particular stat plot. There's several types of plots here. What we want is a scatter plot, and that's the last one. I'm sorry, that's the first one. So it's already on scatter plot for us. Okay. And then we need to tell it where our x values are and where our y values are. The x variable is going to be the independent variable, and the y value is going to be the dependent variable. It's the thing we're trying to predict. In this case, we would think that, well, your height is something that you can't really control. But we would think that we use that to determine what a good weight should be. So the length, I'm going to let be my x values, and then the weight will be my dependent variable. It's my y value. So I had my lengths in L1, and I put my weights in L2. Then I can choose what type of mark I want to use on my scatter plot. And this part doesn't matter really. It's just a matter of preference. So highlight one of the marks. I'll do the plus sign. To use in our scatter plot. Okay, so now let's hit second quit to get out of there. Okay, so now I want to graph this. Everything should be set up. One more thing though, before we graph it, make sure you don't have any equations on your y equals list. Otherwise, those are going to graph along with your data, and we don't want that to happen. So turn off any equations that you might have or clear them out. So mine are cleared out right now. And now I'm ready to graph. I'm going to hit the graph button, and I probably won't see anything. So don't panic. What we're going to do is select the zoom button, and I believe it's option 0. No, option 9 is zoom fit. Okay, so once we know that, we can just hit zoom and the 9 key instead of having to scroll down to it. But zoom 9 will adjust your window so that it can see the statistical data that you're looking at. So looking at this is a plot that shows the heights of the bears compared to the weights of the bears. Okay? And so what we want to see is there a linear pattern? And most things in life aren't perfect. So, we won't often see a very strong line. You can't always expect that. Of course, as we think about it, we know there are a lot of things that go into determining weight besides your height. So we're not going to expect always to see a straight line, but roughly speaking, do we see a pattern such as the heights increases, so do the weights? And I would say yes, we do see that roughly speaking. So eyeballing it, we see it. Some other patterns that we might see would be, let's say, a parabola, or you might see something that was like a sine or cosine curve where the data is going up and down. We're just doing basic linear regression, so we want to make sure we don't see anything other than possibly a linear pattern here. And I say yes, we do. Okay, now that I have that, some people might think, well, I don't know if I see a linear pattern, or someone else might say, I'm not sure how strong that linear pattern is. So the next thing we need to find is the correlation coefficient. The correlation coefficient is the measure of the strength of the linear relationship. It lets us know how strong that relationship is. The values for R range between -1 and +1. Okay? The closer R is to either 1 or -1, the stronger the relationship is. In fact, if it's equal to 1 or -1, we have a perfect linear relationship. And then the closer it is to 1 or -1, the stronger the relationship is. The closer it is to 0, then we have no linear relationship. Okay? So we want to find that correlation coefficient, and we need to do something on our calculator. We'll only need to do it this one time unless you take your batteries out. We've got to turn on the diagnostics. So we're going to do second. We're going to hit the 0 key. This opens up the catalog of all of the functions that your calculator has. Okay, we're going to hit the X inverse key for letter D. That'll give us a jump so we don't have to arrow down so much. And then just hit your down arrow until you see diagnostic on. Okay, once you get to diagnostic on, hit enter and enter again, and that's done. Okay. Now, let's find the correlation coefficient. To find it, we're going to go to Stat. We're going to go over to Calc. And number 4 is linear regression. We're going to select number 4. Now, we have to tell it where our X values are, followed by a comma, followed by where the Y values are. So I put my X values in L1. I'm going to hit the comma above the 7 key, and then L2. Okay, and then enter. Okay, so just about everything else that we need for our regression is done in that one step. Had we not done the diagnostic on, then we wouldn't see R squared and R. Okay, so if you're not seeing R and R squared, that means you need to go and turn your diagnostic on, as we did earlier in this video. But here's R. We get an R value of 0.72, which I would say is a moderate linear relationship. Okay, there's definitely some linear pattern between the heights and the weights of these black bears. Okay, so our correlation coefficient R is 0.72. So yes, we've already visually looked to see if there's a pattern. Now we've done a numerical assessment of whether there is a reasonable or strong linear pattern, and we say that there's a moderate relationship here between the two variables. Okay, so the next thing then is, well, what is that relationship? And A and B help us to say exactly what the equation is that would allow us to make predictions about weight based on the length of these bears. So this is a linear regression. If you think back to your algebra course, we had y equals mx plus b. On the calculator, they're calling it y equals ax plus b, but it's the same thing. So we can say that our equation for the height of these bears is y hat equals 1.74 minus 151. Okay. Y hat equals 1.74 x minus 151. Okay, where x would be the length of the bear and y is going to be the weight of the bear. Okay. Now, we want to make a prediction then with these weights. So it says predict the weight of the bear that is 158, or rather 148 centimeters. So the only thing I need to do on the calculator is say 1.74 times 148 minus 151. And so we can predict now. We have a model that we can use for predictions. Um, and we can say that a bear that has a length of 148 centimeters has a weight of approximately 106.52 pounds. Or was this kilograms? Okay. All right. What about if the bear has a length of 160 centimeters? Okay. Well, if the bear has a length of 160 centimeters, then again, I could just type it in. Or if you want to be, more precise, then we can put that regression equation on our y equals list. I can say y equals, I hit the y equals key, and I'm going to go to vars. Number 5 is statistics. I can go over to equations. And then the first option there is regression equation. So it will paste the last regression equation that was performed on the calculator on this list. Okay, so you see the 1.74, it's got all the extra decimal places, etc. And in fact, while we're here, if I graph this now, it graphs that regression equation with my data so I can see how well the equation fits the particular data set that I have. If I want to use it for making a prediction, I would go to vars and go to yvars by using the right arrow. Okay, we're on function, and so our function was y1, and now I can say y1 at 160 centimeters. And we get 127.9 kilograms. Okay, so let's do one more prediction exercise. This one says to predict the weight of a bear that is 200 centimeters in length. And the first thing you should do, really, before you make a prediction, is to look at the data that we use to come up with the model. Okay, we really don't need to predict for a value that falls very far outside of our observed values. These values for length are values that we actually observed, and we want to make sure that um, we don't go too far beyond our model because the pattern could change. So you can go a little bit outside of it. For instance, when I look at this data, it looks like the minimum value is 120 and about 120, and the maximum value is 166. So, I might feel comfortable making a prediction at 170. I may even make a prediction at 180. But for the example that we're looking at now, it asks us to make a prediction about a length of 200. That's very far outside of my observed values, and the pattern can change. So, what I would say for that particular example is that this model is not appropriate to make a prediction for this value. Okay, it's not appropriate to make a prediction for that value because that particular value falls too far outside of the range of our observed values. I can give you another example of that. Suppose we were collecting data regarding temperature and the amount of money we had to pay for our electric bill. So I'll have temperature. We think temperature has a huge impact the on your electric bill each month, okay, in dollars. All right, so if I start taking um, or recording the temperatures and bills for people who live in our region of the South here, in about March, when let's say the temperature is about 70 degrees, maybe a little less than that, that's when we have the lowest electric bills. Okay, so I might collect data as the temperature increases. I'm going to look at average temperature and the amount of my bill. Okay, and I might see a pattern that looks something like that. Okay, and so looking at just this pattern alone, I might conclude that, hey, once the temperature drops below 70 degrees, then the electric company will start to pay me. And of course, that's not true, right? Once the temperature goes below 70 or below 65 degrees, then we start to see a different pattern, right? We start to see the electric bill go back up again. So if we only made observations for 70 degrees to 100 degrees, then yeah, we might mistakenly think that this is a linear pattern. But once we see the other side of this data, we see that it's more of a quadratic equation instead of just linear. So the point is, when we make a prediction that falls beyond our observed values, we're not sure if that pattern continues. I make a big point about this because this is the most missed question on this test. So when you see a question asking about um, making a prediction, make sure the first thing you do is look at the number to see if it falls reasonably within the range of observed values. And again, for this one, our observed values go from about 120 to 166. And so 200 is too far outside of the range of those observed values to make a prediction. I interpret the slope of the regression model. Okay, we wrote down our model a little while ago. We said that it was something like y hat equals 1.74 x minus 151. Okay. So for the slope in algebra, basically the way that we interpret that is that each time x increases by 1, the slope lets us know how much y is going to increase by. So in this case, what we would say to interpret the slope is for each additional centimeter of length, the weight increases by 1.74 kilograms. Okay? So that's how I would interpret the slope. For each additional centimeter of length, the weight increases by 1.74 kilograms. All right? When it comes to interpreting the intercept, um, in algebra, we find the intercept when x is equal to 0. All right? In this case, x represents length. And so if we went on and made the interpretation, we can see that the value of the intercept is negative 151. If we made the interpretation, we would say that when the weight is 0, the weight, I'm sorry, when the length is 0, the weight of the bear is going to be negative 151 kilograms. That doesn't make sense. And again, the reason that that doesn't make sense in this case is because 0 falls very far outside of the range of observed values. We don't have any zeros in these values that we observed for length. So in this case, the intercept does not have a practical interpretation, and that's what I would say. The intercept does not have a practical interpretation because the weights or 0 falls very far outside of the range of observed lengths. And then the last piece is about determining and interpreting the coefficient of determination. Okay, the coefficient of determination lets us know about the explained and unexplained variation. And we actually already found that on our calculator. Um, it is actually r squared on the calculator. Okay, coefficient of determination is r squared. Okay, r squared is the explained variation. And it actually is r, the linear correlation coefficient, squared. Okay, so if you know the linear correlation coefficient, you can find the coefficient of determination or the explained variation simply by squaring r. Okay, so we get, if we go back to the calculator, it was already on there for us. We can do our linear regression again. I'll just hit second enter, second enter, second enter. That'll take me back to it. And so we had r squared was equal to 0.5258. Okay, so what I can say is that 56%, or about 56%, I'm sorry, not 56%, but 52.6%. Okay. Of the variation in weight is explained by length. Okay? And so that means that about 48% is unexplained. Of course, we'll expect that there'll always be some unexplained variation. That's just randomness or what we call noise in the data. But 48% is a pretty large amount. So in a practical setting, what we would start to think about is what are some other things we could use to add to our model to help us better be able able to predict the weight of these bears. And an example might be age. Okay, we might look at the age to see if that would help us. If we looked at age and length, could both of those things help us improve the model and get better predictions for weight? Or if we went on to some more statistics, we could even look at gender. Okay, so age, weight, or age, length, and gender. Those things could help us all to predict the weight of the bears.